All right, so welcome to another exciting episode. This is for you, Aaliyah. You're the only one absent today. And so today we're going to start continuing and hopefully finishing up most everything about KSP, at least the main things, and kind of looking at the most recent years, 2022, 2023. There really, even on 2024, wasn't a true KSP problem in the free response portion. I'm sure there was some in the multiple choice. They can ask some questions KSP related in multiple choice as well. But we need to talk about, we've talked about the first three types, the common ion problems, calculating the molar solubility in KSP. Today we want to look at question number 4, the fourth type. And on this 2001, when we already did the A, 1, 2, and 3, I want us to look at this B, 1, 2, and 3. So we're actually going to look at 1 and 2. Number 3 is actually the fifth type of problem, which I did not get to in fourth period. But when we look at this, okay, this one's going to read at 25 degrees, the value of KSP for lead chloride is 1.6 times 10 to the minus 5, and silver chloride is 1.8 times 10 to the minus 10. If 60 milliliters of NaCl is added to 60 milliliters of PbNO3, 2. Notice none of those are there, but if I mix those two things together, if I mix NaCl plus PbNO3, 2, what is that going to make? Okay, it's a double replacement reaction. The positive of the first goes with the negative of the second. Positive of the second goes with the negative of the first. So say it again, what are we going to get? NaNO3. Now again, we always balance the charge. So what's the charge on sodium? +1. What's the charge on nitrate? So it's just going to be NaNO3 plus PbCl2. Now, okay, it's saying, will a precipitate form? Well, first off, which one of those two even has the possibility of being a precipitate? PbCl2. Now, we know this for several different reasons. Number one, what do I know about all alkali metals and all nitrates? Always soluble, always aqueous, which tells me that this one must be the solid. But what's another context clue that the lead chloride might be the precipitate? They give you this right here, okay? PbCl2. They don't give you anything for NaNO3. You're obviously not going to make any silver chloride there because you can't just create silver out of nothing, okay? So it's just telling me the PbCl2. So there's my question. So the question is, will a precipitate form, and how do we know if a precipitate will form or not? Okay, well, less than or greater than, what has to be less than or greater than? You're very much on the right track. Okay, what do we solve if it's not in equilibrium? What do we call that product? Q. So we're going to have to calculate Q and compare Q to KSP, to the given KSP. If Q is greater than KSP, what's that going to tell us? If Q is greater than KSP, will a precipitate form or not? This is important for us to know this. What does KSP tell me? What is the whole point of KSP? That's a good question too, right? What's the maximum amount that can be together and stay dissolved? Okay, anything greater than KSP value is going to be insoluble or going to form a precipitate. So if Q ends up being greater than KSP, that means the concentration of those ions exceeds what is able to stay in the solution together. So a precipitate will form. If Q ends up being less than KSP, that means that we haven't maxed out the solution yet, that we still have room for more ions before they begin to precipitate out. Okay? So this will a precipitate form. When you see this, will a precipitate form, that's telling me it's a Q problem. Okay? Now, there's several layers to this. So the first thing I have to know, and you don't have to write this out, I'm hoping that you can look at NaCl combining with lead nitrate. That, okay, I'm just going to swap them, okay? So Sanika did this in her head before, well, I had to actually write it out, but you can just see it's going to make sodium nitrate and lead chloride. Well, lead chloride is what they give me. That's going to be my precipitate, okay? So when I write my KSP expression, how do I write, the equation for the actually calculating Q? Well, how do I write it? How all of our K, when we do all these, how do we write the equilibrium expression? Products over reactants, but what's my equation going to be? Do I use this one? What do I use? So I'm going to want to say PbCl2 going to Pb2 plus 2 Cl minuses. When we do KSP, or even calculate QSP, it's always going to be from the solid going to aqueous. Now, we can flip the equation. Equilibrium can go either way. But when they give you a KSP value, this value right here is always for the equation written this way. Now, if we wrote it the other way, the reality is we're actually going the other way. We're putting Pb2 plus Cl minus, and we're making it go. And by the way, if we wanted to balance this, we balance it like that. But we're making it go the other way. But KSP is always written in terms of this format. If we did it the reverse, how would KSP compare to this number? If we did it Pb2 plus 2 Cl minus went to PbCl2. So if we wrote it reversed, what's that do to K? Reciprocal 1/0. Remember, if we reverse an equation, we take the reciprocal of K. If we multiply an equation, we raise K to that power. And if we add equations together, we multiply the K's. But just so you know, it's always written this way. So now I have to calculate, so Q is going to equal Pb2 plus times Cl minus squared. But now I need my Pb2 plus concentration. That's where this part comes in here. When it's asked, will a precipitate form, it's a two-part question. The first thing you have to do is a dilution problem. Because we're going to mix 60 milliliters of this with 60 milliliters of that. So when they're actually in solution, just like when we did our kinetics problem, once it's in actually mixing, it's in the diluted form. So what's my equation for the dilution? It's MCBC is equal to MdBd, right? So my chloride ion concentration, okay, the chloride is coming from NaCl. So it's 1-to-1, so I can just here, so it's 0.04, molarity, the concentrated is 0.040, and I have 60 milliliters of it, is equal to the molarity of the dilute times, what's my final volume going to be? What's the volume of the dilute going to be? 120, 60 plus 60. Now we can see that if we go from 60 to 120, okay, and that needs to be milliliters, I just don't have room. So the reality is we're going to get 0.040 molar times 60 milliliters over 120 milliliters. which is actually obviously going to be 0.020 molar. So it's going to be half, because we're going from 60 to 120. So we got to do the same thing for the lead. Now again, it's 1 to 1. It's one lead, whatever this is. So we're going to say for the PV2 plus, I'm just going to go to the shortcut. I'm just simply going to say 0.030 times 60 over 120 is equal to 0.0150 molar PV2 plus. And this is Cl minus. So now what do I do with those numbers? Plug them now we plug them into Q. Now we know our PV2 plus and we know our Cl minus. So now we're just going to plug in 0.015. That's lousy, 0.015. 0.015 times 0.020. Be consistent. Molar squared. And what's that equal? Okay, so I got my diluted concentration, so now I'm just going to use those to calculate Q. This is 2001, down at the very bottom.
Zero. Wait, do you want it in scientific?
It doesn't matter, but it's probably easier in scientific notation.
Okay. I got 3 times 10 to the negative
3.0
4th.
times 10 to the minus 4th.
Mm-hmm.
That doesn't sound like what somebody got.
Oh, I didn't swear. That's
Okay.
6 times 10 to the negative 6.
6 times 10 to the minus 6th. Okay. So what do we do with that value? That equals Q. Compared to K, the given K, and is Q greater than or less than K?
Less than.
Q's less than K, so what does that mean? Will a precipitate form or not?
No.
No precipitate. So we say Q, I would even say since Q is less than KSP, no precipitate will form.
When we're doing the explanation, do you want us to also show the numbers when we do Q's less than KSB, or is it?
You don't have to. I mean, if you show your work right there and you label it Q, and K is there, so you can say Q is less than KSP. All right. So when it's asking, will a precipitate form, or what are you going to observe? Are you going to see anything? It's find. You got to calculate Q, but in order to calculate Q, you got to find the diluted concentrations. So we're going to do 2 more of these. Okay. Right fast. It's all right. Nobody else in the room is in a hurry. Except me. I'm just going to get recharged. Got it? Okay. So turn it over now. I think we're going to go to 2006. we're gonna go, not to turn it over, we're gonna go to year 2006. Wherever my 2006 ended up at, right here. Now look at D. Now this one's easier because it only gives you one thing. But it says the value of KSB for the salt barium chromate is 1.2 times 10 to the minus 10. When 500 ml sample of 8.2 times 10 to the minus 6 molar barium nitrate is added to 500 milliliters of 8.2 times 10 to the minus 6 sodium chromate, no precipitate is observed. Assuming the volumes are added, calculate the molar concentrations of barium and chromate. So how do we calculate the molar concentrations of the barium and the chromate in the solution? Can you tell me what they're going to be just doing mental math? No? Nobody? Sam, what are you going to get?
They're both just half.
They're both going to be half, right? How do I know that? Because it's going to be 500 plus 500, so they're equal amounts, so you're just diluting it in half. So to do part one, we can simply say, and you need to do it for each one. So we want to know the barium concentration. Okay? It's going to equal 8.2 times 10 to the minus 6 molar. And all you got to do is say times 500 over 1,000. That's going to come out to 4.1 times 10 to the minus 6 molar. So you do the exact same thing for the chromate. Now, there's all kinds of discussions in the other class of, can I just show this or can I just show that? Look, don't try to take a shortcut that when you have an easy problem, just show that. That didn't take that long just to show the work. And that's so easy for a grader, grade plus, this might even be +2. It might be +1 for that and +1 for that. Who knows? Okay? So that's just easy money right there. Just calculating anytime you dilution. Now look, this is the MCVC equals MDVD equation. Molarity of the concentrated times the volume of the concentrated equals the molarity of the dilute times the volume of the dilute. Well, to get this number, we divide it through by the volume of the dilute, 1,000 milliliters, and to get the molarity of the dilute. So, I mean, anytime you do a molarity problem, it's always just going to be whatever the ratio is of the initial over the final. Okay? Most of the time lately, it's been just half. It makes it easy. You can almost do it in your head. Well, you can do it in your head, but you got to show the work. Okay? So now part 2, use these molar concentrations to determine above to show why a precipitate does not form. So what do we have to calculate? Q. So they don't have the equation, so even though it's not required, what would the equation, the dissociation equation, be for barium chromate? Kind of need it to be able to write your equilibrium expression, but you can do it in your head if you needed to, but I mean, what are we going to get? Okay, just Ba2 plus the CrO4 minus. Therefore, Q is going to equal what? What times what? Ba2 plus times my CrO4 minus, which since they're both the same, it's going to be is equal to 4.1 times 10 to the minus 6 molar squared. Which you've got what, 1.7, 1.8. What does it come out to?
I
Well, you gotta get confident, you gotta know how to use your calculator.
know, I just keep plugging things in.
Sometimes 10 to the minus 11, but now you have.
I got 1.7 times 7 minus 11.
Okay, so now what's the significance of that number? What do we do? Well, how do I know? Come back to the question. You use these concentrations to show why a precipitate does not form.
You compare it to K.
You compare it to K. Is it greater than or less than K?
Yes.
Okay, here's the given K. K is times 10 to the minus 10th. This is 10 to the minus 11th. Okay, since Q is less than KSP, no precipitate formed. Okay? So you have to do the dilution to find what the diluted concentrations are, but that's a really simple calculation. Initial concentration just times the ratio of the initial times divided by the final, and then use those to set the KSP. Now, the thing that's always, you have to know that we're dealing with this equation, that Q is gonna be set up this way. Anytime you have a KSP problem of any kind, it's the solid going to aqueous. That's the way you write your equilibrium expression. Okay? So now let's look at one more then. Same packet. Same packet. It's let's look at, it's the last page one, I think it, I didn't put a year on it, but it's this one where we have the, I'm gonna get all kinds of questions off of this one. Well, I guess we can just work our way down. I didn't do it this way, but let's just work our way down here. I can't remember what year this was, I didn't mark it. But somebody was in a bad mood when they wrote this question. Okay? So, several reactions are carried out using AGBR, cream-colored silver salt, for which the value of the solubility product constant is given as 5 times 10 to the minus 13. So write the expression for the solubility product constant KSP. Okay? So go ahead and just do that. You should be able to do that. Right, that should take you all of about 10 seconds. So KSP is going to equal what? Now, even though it doesn't ask for this, a lot of times it asks for, write the equation for the dissociation of silver bromide. So what would the equation be? It's going to be AGBR, solid, going to what? AG plus BR minus. Now look, so many times in years past, this simple equation, people trying to add water into it, AGBR plus water, and then trying to do all kinds of stuff. It's just the simple dissociation. The aqueous tells me there's water there, okay? Just keep these equations simple. Okay, I know there's gonna be a big gap between now and May when you actually take the test, but it's always going to just be this equation. So write the expression, calculate the value then of the silver ion concentration. So how do I find the silver ion concentration here then? What do I know? Here's my equilibrium expression. What do I already know right now? I know KSP. So what are these two values going to equal? X and X, right? So if I'm going to have X amount of this one, I'm going to have X amount of that one. So it's simply going to be 5.0 times 10 to the minus 13 is equal to X times X. So you just take the square root. So X is equal to my Ag plus concentration, which is going to equal, I'd say 7.0, 7.1 times 10 to the, that's going to be negative 7. So 7.0, 7.1. Okay, so that's my concentration on my silver ion. It's also my bromide concentration. It would also be the solubility. We are finding the molar solubility here. What does molar solubility mean? Yeah, it's the solubility in terms of molarity. Okay, that's what we're finding. So the silver ion concentration is this, the bromine is going to be that, but for every one of these, you're going to, the solubility to AgBr is also that value. Okay? Now here's the tricky question. Now what is the significance of 50 milliliters? Is that, do we have to figure that in anywhere? Because we're measuring concentration, right? So if I have a 1 liter bottle of something and I pour out 50 milliliters of it, is the 50 milliliters going to be any different concentration than the original concentration? No. The ratio is moles per liter, but you don't have to have a liter of it to have molarity. So I mean, I have this is 0.25 molar K2CrO4 right here. I definitely don't have a liter of it, but it tells me the ratio of what it's going to be. So the 50 milliliters is totally a distractor. Okay? Totally irrelevant. Doesn't matter whether you have 50 milliliters, 500 milliliters, 5,000 milliliters. It's always going to be a saturated solution. The maximum that can dissolve is going to be this much. Okay? So it's always going to be the same concentration. The KSP, the only thing that's going to change this number is going to be the temperature. So that was one distractor in here. So, okay, so we have a simple problem, but they put that distractor in here. The 50 milliliters really means nothing. It wouldn't matter if it's 50 milliliters, 100 milliliters, the volume wouldn't matter. Now, 50 milliliter sample of distilled water is added to the solution. So now I have this. So now I'm going to add some water to it. But listen to read. I can do this. Let's read what it says next. Which is in a beaker with some solid AgBr in the bottom. So we already had some solid in there. The solution is stirred, equilibrium is reestablished, and some solid silver bromide still remains in the solution. So it's still a saturated solution. Well, what's the concentration going to be of a saturated solution? That. We didn't change anything. Now, let's talk about what's going to happen. You put water in, okay? What happens to these concentrations initially when you put the water in? They go up or down? Add water. It's getting more concentrated, less concentrated? Less concentrated. These numbers go down. It becomes more dilute, right? So now Q is suddenly less than K. So what's the reaction going to do? Shift right. Now look, common sense. You put more water in, more is going to dissolve. We go to the Le Chatelier's principle. Adding water favors the side with more moles of dissolved ions. Adding water is going to favor this side. More is going to dissolve. Okay? So these concentrations went down. Now for every one of these, one of these comes into solution. When is equilibrium going to be reestablished? We said Q initially went down. When's the equilibrium gonna be reestablished? When Q equals K again. Well, when's Q gonna equal K again? When silver is back to that. And for silver is back to that, the bromide's gonna be back to that. Right? So more is gonna dissolve. As long as there's still some sitting in the bottom, more is gonna dissolve until it gets back to where it was before, because the only thing that's gonna change these numbers is temperature. Okay? Now, that was kind of a tricky question, because your natural instinct is to say, well, I dump water in, it's gonna be less dilute, it's gonna be more dilute, the silver ion concentration is gonna go down. Well, it is initially, but it's gonna come back until it gets back to where it was, because a saturated solution is always gonna be the same concentration no matter how much you have. As long as there's some sitting on the bottom, it's always gonna get back to where it was before. Alright, so now let's look at D. Well, actually, I'll give you a chance to write that down. Beginning class tomorrow, you juniors are going to go to college and career instead of coming here for AO. You'll go straight at 12:35 to college and career. Okay. Assuming Aaliyah decides to come back to school, somebody needs to tell her too. Okay. Aaliyah, you need to go straight to college and career at 12:35 tomorrow. Y'all know where that room is, right off you guys. Alright. Does everybody understand this? Okay?
So is it because there's still some solid?
Yeah. So it's still gonna be a saturated solution, and a saturated solution at the given temperature is always gonna be this concentration. Okay? So, I mean, if you wanna go into further detail, you can say, initially, the concentrations of Ag plus and Br minus are decreased, therefore Q is less than K. But the equilibrium will shift to the right until Q once again equals K, which will cause the concentration to be the same as they were before. Okay, so that was kind of a tricky question right there, just kind of what's going to happen, kind of playing with your mind. Now, calculate the minimum volume of water in liters necessary to completely dissolve 5 grams of AgBr. Well, what's the concentration of a maximum amount, the saturated solution? What's the concentration going to be of that AgBr? 7.1, right? So my molarity, okay, my molarity is equal to 7.1 times 10 to the minus 7 molar. Well, what does molarity equal? Moles over liters, right? Well, what is the question asking for? Liters, right? The minimum volume of water, okay, to dissolve 5 grams. Well, I got to change that 5 grams to, how do I change the 5 grams to moles? With the molar mass, which they gave you. So it's going to equal 5 grams divided by the 188 grams per mole divided by L is all going to equal 7.1 times 10 to the minus 7 molar. So obviously the L and the 7.1 are just going to change spots, right?
Do you not use the 5.0? Because wouldn't that be for the AgBr?
No, this is your KSP value. That's not the concentration. The concentration we found, the Ag plus, is this, but for every one of those dissolves, so that's my AgBr concentration. So don't confuse KSP with the molar solubility. So again, one of them you're given KSP and you have to find the molar solubility. The molar solubility is what you're gonna use. So liters turns out to equal to 2 sig figs, not 35, 37. So what you guys got is 37,543 or something like 453 or something along those lines. Now, this was a problem because I remember the year when when they did this, everyone came out and said, oh man, that can't be the right answer. They spent a lot of time on this one because they said, there's no way it's 37,000 liters of water. That can't be right. I must be doing something wrong. So I'm saying somebody must have been in a really bad mood when they wrote this, because they're putting all kinds of tricky stuff to kind of mess with your head all in the same problem. Okay? So yeah, to get 5 grams to dissolve 37,000. So what does that tell me about the solubility when you have a KSP of 10 to the minus 10th? What is that? Or minus 13. You're not gonna get much. 37,000 liters is a lot. It's like a swimming pool. Okay. So that was crazy. So now E. E is really the problem I was trying to get to. These are all good. These are all just KSP type problems and kind of combining everything together. But why don't you try to do E right now? You go ahead and pause the. All right, so when we're looking at this, what did you say the student will observe? A precipitate will form. Okay, and how did we prove that?
Q is greater.
Okay, so we have to go through, we have to, for E, I'm going to just move this up so I have some board to write on. Okay. So the first thing we have to do, now look, I combine AgNO3 and NABR. What's my precipitate going to be? AgBr. Now, of course, they give you all the stuff about AgBr. Everything's been about AgBr, so hopefully context clues is telling you, hey, I'm finding out if AgBr. So I have my AgBr solid going to Ag plus aqueous plus Br minus aqueous. So there's my expression. So Q is going to equal Ag plus times Br minus. So I need to find those diluted concentrations. So I can say my Ag plus, how do I find that? How do you find the Ag plus? Okay, so I start with the concentration that's given, 1.5 times 10 to the minus 4. And what do I multiply it by? 10 over 12, right? Because I start with 10, but I'm going to end up at 12. So 10 12ths, and that's going to end up equaling to 2 sig figs. That's going to be
1.3 times 10 to the negative 4.
times 10 to the minus 5.
It's minus 4.
Minus 4. You guys talk so softly, I can't ever hear you. Okay, so now I have to do the same thing for my Br minus. The Br minus is going to be 5.0 times 10 to the minus 4th molar times what? 2 milliliters over 12. And that turns out to equal?
8.3 times 10 to the negative 5.
Thank you. Okay, so now what do I do with those numbers?
You do the Q.
Now I just plug them into my Q. So it's going to equal 1.3 times 10 to the minus 4th times 8.3 times 10 to the minus 5th. So Q is going to equal
1.1 times 10 to the negative 8.
I don't like it. Times 10 to the minus 8. Okay? But she's speaking with boldness, and then finally, so I can hear you guys always just talk so softly.
So it's like in case of
All
roll.
right. I know, you got, come on, I'm confident, I believe in myself. So now what do I do with that?
And then you compare it to K.
Now I compare it to the given K. The given K is somewhere up there, the given K.
It's 5.0 times 10 to the negative 13.
Okay, so that's given. So Q is greater than K. So since Q is greater than KSP, the student will observe, I'm answering the question, a precipitate forming. The formation of a precipitate. Anything saying the student's going to see a precipitate. But you have to prove it with Q. All right? I know, we're having so much fun with these, we just got to keep on going. Everybody got that? Aaliyah, you got that? Okay. Somebody over in Russia is going to say, who's Aaliyah? Who's Aaliyah? Back to 2004. Looking at the bottom of 2004. Okay, I'm just going to, for the sake of time, I just want to kind of go through this one pretty fast. So we're going to write the balanced equation for the dissolving of silver phosphate in water. Now this is again where students get messed up because they feel like they need to include the water. But what's the equation going to be for silver phosphate dissolving in water? What am I just going to put?
Like the value of the equation is going to be 3 Ag plus, and then PO4 3 minus.
PO4 3 minus. Now, I've said it over and 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 over again. If you do not put the charges on those ions, then you do not get credit for that equation. Silver will not dissolve in water. If it did, your jewelry would dissolve every time you wash your hands. Okay? They dissolve as ions. Ionic compounds dissolve as ions. Okay, so you got to include, now you do not have to have the states. The solid and aqueous are not required. Charges are always required. Okay? Now, so now that's that. So now they tell me that the silver ion concentration is 5.3 times 10 to the minus 5 molar. So what's the phosphate ion concentration going to be? A third of that. Okay, so they kind of went the other way. It's, you know, they gave you the 3x instead of the x. Okay, so a third of that is going to be 1.7 times 10 to the minus 5 molar. I think it's actually it's 1.8, isn't it? 1.7666666, so 1.8 times 10 to the minus 5th molar. So now I can calculate my KSP, because KSP is going to equal silver ion concentration cubed times my phosphate, which is going to equal 5.3 times 10 to the minus 5 cubed times 1.8 times 10 to the minus 5. So it's all going to equal anyone?
9.5 times 10 to the negative 10. Oh.
Did anybody?
Hold on.
No?
No. I mistyped. This is why I don't answer.
I got 2.7. That's what I got.
2.7 times 10 to the minus
18.
I think
Mhm.
18,
Wow.
2.7
What am I doing?
times 10 to the minus 18. Okay, so a very tiny KSP, not a whole lot, it's not very soluble at all. Okay? Now this is the part that I really want to focus on though. Do we not get that?
I don't know. Oh, I wrote it down.
Okay, we gotta do better at not making any careless mistakes. So now it says a 1 liter sample of the saturated silver phosphate. So we have a saturated solution of this, meaning you got some solid sitting on the bottom. That's what saturated always means. You got the maximum amount dissolved. You gotta have, in order to have this equilibrium, you gotta have some on both sides. So you're gonna have to have a solid over here still on the bottom. Okay? The water is allowed to evaporate until we get down to 500 milliliters. So as the water evaporates, what's that gonna do? What are we gonna observe? We're already saturated. We're saturated at this concentration. So if water begins to evaporate, what has to happen?
More precipitate.
It's got to go left. It's got to precipitate. Just like adding water favors the side with more moles of dissolved ions, removing water favors the side with fewer moles. And it just makes sense. There's less water. So now what's happening, okay, so if you evaporate the water off, so there's less water and the same number of moles, what does that do to Q? As the water evaporates, what does that do to these? If I go from 1,000 milliliters to 500 milliliters, what, assuming none precipitated out, what would be the case here with Q? It's going to be way bigger, right? These are going to be double the concentration than they were before. Now Q is way greater than K. So the reaction has to shift left to get Q equal to K. So then when equilibrium is reestablished, what's going to be true about these numbers? They're going to be the same. Because a saturated solution, no matter whether you have 500 milliliters or more, okay, it's going to be the same. Because it's still saturated. So more is going to precipitate out until it, because this is telling me the maximum amounts that can stay together. Now I've seen the question asked in a different year the other way, is what happens to the concentration if you go from 1 liter to 2 liter. You have 1 liter saturated solution, you add in water till you go to 2 liters, but there's still some sitting on the bottom. This is very much like the last one we just asked. Still some sitting at the bottom, what's going to happen to the concentration? Well, it's initially these are going to go way down. Q is now less than K. The reaction is going to shift right until it gets back to where it was before. So removing water, adding water, as long as there's still some sitting on the bottom, you're going to always have the same concentration as long as you're at the same temperature. Okay? That's a key concept. Key concept right there. All right. I know you guys are tired and you're ready to quit, but I'm not. I want to look at now, the last thing I want to look at are the more recent, okay? So we're going to go to year 2024, okay? 2024, the second, I think it's the second to last page. No, not that one. We're going to go to 2023, the last page, well, the front of the last page, 2023. Okay, and we're going to love it if they will ask a question like this one. Answer, let's take like 3 minutes to answer this one.
Oh, it's another.
It's a different packet. It's the packet I gave you before for all the equilibrium problems. It's that one, yeah. Go ahead and pause the error. It just says identify the error. Does it say explain? What's the error?
It's not a OHs.
There should be twice as many OHs because the equation is a 1 to 2. So you just, the error is there should be, twice as many OH minuses, or there should be 4 more OH minuses, anything along those lines, okay, because it's a 2-to-1 ratio. But you don't have to go into a big long explanation of why that is, because it simply says identify, it doesn't say justify your answer. Okay? Number 2. So now we go down to here, okay? So no more solid dissolves, and the student determines that SO3, SR, so we already determined up here, and this is given, that the SR OH2 goes to SR 2 plus 2 OH minus. So if it turns out that this is 0.043 molar, what do we know that is? 0.086, right? So it says calculate the value of the OH minus. So to show the work, I would go 0.043 molar SR2 plus times 2 moles OH minus for every 1 mole SR2 plus is equal to 0.086 molar. Now, it's such a simple calculation. You may just be able to go times 2 equals, you know, because a lot of times if it's just implicit, you know, as long as if they see this, but this is the best way to kind of show it right there. And then lastly, calculate KSP. Well, KSP is going to equal SR2 plus times my OH minus squared. So we already have those, so it's going to be 0.043 times the 0.086 squared is going to equal to 2 sig figs. 3.2 times 10 to the minus 4. Hey, that is 4 easy points right there. We love that question. Okay, no tricks, nothing, where you have to kind of read into anything. I mean, it's just as straightforward as it comes. All right, so that was 2023. We really don't have time, but we'll look at 2022. 2022 on the back. Number 7, the very last question. And we'll talk about part B3. Let's see if you can do A, B1, and 2 just real fast. Okay, so we'll just pick up there tomorrow. All right?